Swayam Prabha. Digital India. Educated India.
In the previous lecture, we saw how Couette flow model can be applied to discover effect of property variations through the ratio of molecular weight of the mixture in the infinity and W states. As much as the result we obtained was approximate, it did showed the correct tendency that G over G star of the variable property varies directly with m w divided by m infinity and raised to some power, of course. Today, we are going to look at Reynolds flow model and its applications. In fact, in the next two lectures, I will be dealing with the Reynolds flow model. The first of which today will deal exclusively with air water vapor system, which requires use of psychrometry and steam tables. And the problems that I shall consider are shown here on this slide. The wet bulb thermometer, the measurement of relative humidity in a ducted flow, where we shall estimate the true vapor concentration or the RH, allowing for effect of radiation and without effect of radiation. Then we will consider evaporation from a porous surface and then evaporation from a lake, and then whereas all these problems are of external flow, we will turn to internal flow, in which we will try to humidify air which is entering into a tube whose walls are maintained wet. So, all these problems will require use of psychrometry and or steam tables, as we shall go on to see. So, let us look at the first problem. Here is a problem. A wet bulb thermometer records 15 degrees centigrade when the dry bulb temperature is 27 degrees centigrade. Calculate A, the relative humidity of air, and B, compare with carrier's correlation. Assume Lewis number equal to 1 and take Cp vapor equal to 1.88 and Cp air equal to 1.005. Now, of course, this problem can be solved using psychrometric tables. It can be solved by using what is well known carrier's correlation, but we shall apply our Reynolds flow model. So, here T w is 15 degrees centigrade and T infinity is T dry bulb equal to 27 degrees centigrade, and we have said Lewis number equal to 1, and therefore, B m, which is omega V infinity minus omega V w over omega V w minus omega T, which is 1, it will equal Spalding number calculated from mixture enthalpies as given here. Now, of course, wet bulb records its temperature when the heat conduction to it is 0, and therefore, Q L in our formula will be set to 0. If we take T ref equal to 0 degree centigrade, then lambda ref, the latent heat, is 2503 kilojoules per kg, and from steam tables we would readily discover from partial pressure the value of omega V w. The way to do this is the following. So, for example, since you know T w is equal to 15 degrees centigrade, you will read P sat 15 from steam tables, and then you will evaluate the specific humidity, which is 0.622 times P sat divided by P total minus P sat, and then you will evaluate omega as W over 1 plus W. So, if we carry out these calculations, you will see omega V w turns out to be 0.01068 as I have shown on the slide here. So, if we calculate now the mixture enthalpy in the infinity state, it will be 1.0025 into 27 plus 1.88 minus 1.005 into 27 plus 2503 into omega v infinity. HMW will be likewise 1.005 into 15 plus 0.875 into 15 plus 2503 into the omega v w, which is 0.01068, and that will give you 0.41.95. Here we did not know omega v infinity, and therefore, it is left as it is. HTL is the enthalpy of the transfer substance, which is water, in the L state, that is just inside the WW surface, and that would be Cp of the liquid multiplied by Tw. So, 4.187 multiplied by 15 gives you 62.805. Therefore, equating Bm with Bh, we will have omega v infinity equal to minus 0.0168 divided by 0.0168 minus 1 equal to all this 27.135 plus 2562.2 omega v infinity minus 41.95 divided by 41.95 minus 62.805. If we solve now for omega v infinity, we would get omega v infinity equal to 0.005936, which gives us specific humidity equal to omega over 1 minus omega equal to 0.00594 at 27 degrees C. Now, from psychrometric chart, this value corresponds to relative humidity of 27%, which is our answer A. Also, Bm is Bh and very small. If I substitute this value here, then you will see Bm and Bh would be equal to 0.00479, which is very small. Now, if we use Carrier's correlation, which you have used in your undergraduate work, it gives P v infinity equal to P sat W minus P tot minus P sat W, T wet bulb minus T dry bulb, 155 minus T wet bulb, where T's are given in degree centigrade. Now, in our case P tot is 1 bar, WW is of course 0.01068 minus this value, which is 0.0108, and P sat W is 0.01736 bar, which can be read from the steam tables as well. Then substitution gives P v infinity equal to 0.0097, and therefore, I can evaluate omega v infinity as P v infinity into 1.61 into P tot minus 0.61 P infinity equal to 0.00604, which is answer B. Now, you will see this value of 0.00604 is very close to the value 0.005936 that we obtained from Reynolds flow model, and therefore, we can say that the Reynolds flow model is very well captures the psychrometric relationships. Let us now turn to the second problem. It is given like this: moist air flows through a duct whose walls are maintained at 50 degrees centigrade, and wet bulb thermometers placed in the duct records the dry and wet bulb thermometers located in the duct show 70 degrees centigrade and 25 degrees centigrade respectively. So, we have a duct whose wall is at 50 degrees centigrade and moist air is flowing through it. We have the dry bulb equal to 70 and we have the wet bulb equal to 25. Now, it is also given that the heat transfer coefficient H cof V W equal to 0 for this situation of the bulb is measured as 17.5 watts per meter square Kelvin. So, under this situation, you are asked to calculate relative humidity of air without radiation and B with radiation. So, in the first part, we assume that whatever the wet bulb and dry bulb thermometers are reading are correct values, and they are not influenced by radiation between the tube wall temperature and the bulb temperatures. So, straight away we can see that in this case, corresponding to 25 degree centigrade, we will get WW the specific humidity as 0.02, and therefore, the mass fraction at the surface of the wet bulb thermometer would be 0.0196, which gives us mixture enthalpy as 74.61. HTL will be 4.186 into 25, giving 105.7, and H infinity would be 70.35 to 564.25 into omega V infinity. And therefore, equating BM with BH, we would simply get that relationship, from which we get solving, we would get omega V infinity equal to 0.001446, and B itself would be 0.0185. And since omega V infinity is 0.001446, we can readily recover V infinity from the relationship I have shown on the previous slide as 0.002328 bar. And from the steam tables, PV sat corresponding to T infinity equals 70 degree centigrade, which is the dry bulb temperature, would be 3119 bar, and therefore, relative humidity will be the actual value partial pressure divided by the saturation partial pressure, and which gives us 0.746% as the relative humidity when radiation was neglected. So, that means, the moist air has moisture content of 0.746%. But now, we wish to allow for radiation. Does that make any difference to the estimate of relative humidity? Let us look at that in the next slide. In this part, at the wet bulb, as usual, QL will be 0 and HTL will be HT plus Q rad by NW. You will recall, we account for Q rad in the neighboring phase, and therefore, HT will be Q rad divided by NW, and therefore, BM would be still omega V infinity by omega VW minus omega VT equal to HM infinity minus HMW over HMW minus HT, which would transform to HM infinity minus HMW over HMW minus HTL plus Q rad by NW. Now, this relationship you already know, we have derived this when discussing the Reynolds flow model. Now, the first thing we must do is we must determine the true air temperature, that is the dry bulb temperature of the air, because the dry bulb temperature itself is influenced by the effect of radiation. So, we will say the heat transfer by convection to the dry bulb thermometer, which is H coff into T A true minus T dry bulb, will equal radiation from the thermometer bulb to the wall. So, sigma into TdB raised to 4 minus Tw raised to 4. Of course, we have assumed the emissivity of the bulb to be 1. Now, H coff has been given to you at 17.5. So, Ta true minus 343, which was 70 degree centigrade, equal to 5.67 into 10 raised to minus 8, which is the Stefan-Boltzmann constant, into 343 raised to 4 minus the wall temperature, which is 50 degrees or 323 raised to 4. So, which gives us Ta true equal to 352.6 K equal to 79.6 degrees centigrade. So, remember, in this case the dry bulb temperature itself was not reading correctly, and the true air temperature is in fact 79.6 degrees centigrade. The correspondingly then, what would be the Q rad? Q rad will be sigma at the Q rad at the wet bulb thermometer will be Tw raised to 4 minus T wet bulb raised to 4, and that would be equal to 5.67 into 10 raised to minus 8 into 323 raised to 4 minus 298 raised to 4, which is wet bulb temperature of 35, and that will give you 170 watts per meter square. So, now we must evaluate Bm and Bh freshly, because now we are going to introduce this Q rad in here. Now, we already know that B is going to be very, very small. So, I can replace NW equal to GB, and that is what I have done on the next slide. So, if we take T ref equal to T wet bulb equal to 25, so that lambda ref will be 2442.3, then HM infinity will be CPA into TA true minus T ref, CPV minus CPA into TA true minus T ref plus lambda ref omega V infinity, and that would be 54.52 plus 2490 omega V infinity. HMW of course, because these specific heat sensible heat terms go out, and you will have omega VW into lambda ref equal to 0.0196, 2442.3, 47.87, and the liquid enthalpy would be CPL into T wet bulb minus T ref equal to 0, because we have taken the reference temperature at the wet bulb itself. Now, taking omega mean equal to 0.0196 plus 0.001446. Remember, we had evaluated here omega V W equal to omega V infinity equal to 0.001446. So, we assume that that will still remain the same as far as omega mean calculation is concerned. So, that CPM is not too seriously affected by this choice, although we do not know this value. This is simply to avoid iterative solution, because CPM will not be influenced too much by the value of omega V in the infinity state. So, omega mean is taken as 0.0105, and therefore, CP mean is taken as 1.041. G star would be H coff divided by CPM, which is 70.5 divided by 1041 equal to 0.01725 kg per meter square second. So, now since B is expected to be small, Q rad by NW will be Q rad by G star B. So, that we get B equal to omega V infinity minus omega V W minus omega V T, which is 1, equal to HM infinity minus HMW minus Q rad by G star over HMW minus HTL. Substitution will show on the next slide. Q rad by G star is 0.17 as we calculated here, 170 watts per meter square. So, in kilowatts per meter square, it would be 0.17 into divided by 0.01725 equal to 9.885 kilojoules per kg, and therefore, our balance equation would read like that. If you solve this equation, you will get omega V infinity equal to 0.001693 instead of the previous value of 0.001446. So, as I said, our value of CPM is not going to be seriously affected, which gives B equal to 0.01826. So, our assumption of small b is verified. From this value of omega V infinity, we calculate specific humidity as that, and therefore, P V infinity equal to 0.00264 bar, but P sat at 79.58 is 0.4739 bar, and therefore, the relative humidity now is 0.557% instead of the earlier value of 0.746%, as you can see here. So, the effect of radiation is actually suggests that the moist air is in fact drier than what ignoring radiation would predict. So, the true RH is lower than that predicted by neglecting effect of radiation. Now, these kinds of calculations are very, very important, because often when the so called dry air is supplied, it is never really completely dry. There are very small fractions of moisture, and one wants to know what that small fraction is. And you can see, by allowing for effect of radiation, we have shown that there is in fact significant effect of radiation from 0.746% down to 0.557%, which would be predicted radiation was accounted. So, with this I turn now to the next problem, and here it is. This is of evaporation and a case of high B, as we shall see. Air at 1 bar and 27 degrees centigrade and 90% RH flows over a porous flat surface, which is kept wet by supplying water. The plate temperature is to be maintained at 82.5 degrees centigrade. Now, of course, when you supply water, the cooling would take place, and if you want to maintain the temperature of the plate at 82.5 degrees centigrade, then we may have to supply some heat from the rear side of the plate. So, we want to calculate the evaporation rate and heat flux to be supplied. Now, problems of this type arise in food processing typically, where some material processing, where you want to maintain the surface at a given temperature for whatever the subsequent processing is. So, we are given here in this problem a plate whose length is 0.33 meters and whose width is 1 meter. The air is flowing over this plate, and it is at 27 degrees centigrade and 90% RH, and the wall temperature T w is to be 82.5 degrees centigrade, and we want to find out what should be the Q L to be supplied and what will be the evaporation rate N w from this plate. So, that is really the problem. Now, the U infinity is given as 3 meters per second. The plate is porous, and we shall calculate now. First of all, we must ensure whether the boundary layer is going to be laminar or turbulent or transitional, and so on and so forth. So, first of all, we calculate the plate Reynolds number from the properties that are given here. 3 into the plate length divided by the kinematic viscosity 0.103 divided by 3600, nu is given as 0.103, which will give 34,600 Reynolds number, which is of course less than 3 lakhs, and therefore, we expect this to be a laminar boundary layer with Prandtl number equal to 0.103 divided by 0.153 equal to 0.673. The Schmidt number will be 0.636, and therefore, the Stanton number relationship for a laminar boundary layer is 0.664 REL to the minus 5, 0.5 Prandtl to the minus 0.67. You will recall this was the solution we developed from similarity solutions, and that would be equal to 0.00465. And since Prandtl number is very close to Schmidt number, we can readily say G star will be H cough divided by CPM, which is H rho m U infinity into Stanton number, and that rho m is 1.37. In this case, U infinity is 3, 0.00465 is the Stanton number, and that gives us 0.0191 kilograms per meter square second. So, this is the value of the G star which is operating at the surface. So, now in order to calculate the mass transfer rate, we must calculate the value of B. So, from the data given, P V infinity will be 0.9 into P sat at 27 degrees centigrade, which is 0.9 into 0.03567 bar, and that would be equal to 0.0321 bar. And omega V infinity therefore, can be readily calculated from our formula, and that would be equal to 0.02018. Similarly, P sat 82.5 degrees centigrade, which is at the wall, 0.5261 bar, and therefore, omega V w will be 0.4081, and therefore, B will be simply omega V infinity, which is 0.02018 minus 0.4081 divided by 0.4081 minus 1 equal to 0.6554. So, this is a considerably large B in an evaporation problem. Normally, evaporation problems have very small B, and therefore, we now follow the Reynolds flow model, in which we are advised that G over G star ln 1 plus B should be multiplied by Prandtl by Schmidt raised to 0.33, and also the property correction m mix W divided by m mix infinity raised to 0.67. Now, here m mix W at the wall state, knowing omega V w, we can evaluate m mix W as 24.51. M mix infinity would be evaluated as from this value of 0.02018 as 28.76, and therefore, substitution would give G equal to G star into 0.7039 equal to 0.01344 kg per meter square second. And hence, the evaporation rate from the plate will be G times B into area of the plate, which is 0.01344 into 0.6554 into 0.33 into 1, which is the width, equal to 0.0029 kg per second, or 10.646 kg per hour would be the rate of evaporation from this porous surface. The next thing is how do we keep the surface at 82.5 degrees centigrade, and to do that we will proceed to the next slide. Now, in this case Lewis number is equal to 1, and therefore, B which is equal to H m in B calculated from enthalpy will also be equal to 0.6554, and therefore, we have H m infinity minus H m w over H m w minus H T L plus Q L divided by N w equal to 0.6554, and if I take T ref equal to 0, then Hm infinity would be simply that 78.12, because I know omega VW as 0.02018. I can calculate Hm infinity, and I can calculate HMW also as 1133.85, because I know omega VW, and HTL will be 0.4 into 1.187 into 82.5 equal to 3/4. So, hence QL divided by NW will evaluate to minus 2400 kilojoules per kg, and the negative sign here clearly indicates that heat must be supplied, because we take QL away from the plate into the transferred substance phase as positive, and therefore, negative sign implies that QL is to be supplied to the plate, and therefore, if I now multiply by, therefore, Q supplied will be simply MW, which was 0.0029 into 2400 will give me 6.98 kilowatts. So, for this plate of 0.33 meters by 1 meter, we will need to supply about 7 kilowatts of heat to maintain it at 82.5 degrees centigrade, which is the requirement, the process requirement. Let us now turn to the next problem. A 10 kilometers per hour breeze at 40 degrees centigrade and 20% RH, a situation something like middle of India, say Nagpur or somewhere, blows over a lake whose water temperature is at 30 degrees centigrade. The lake also receives solar radiation of average, let us say 500 watts per meter square, average for the day. So, calculate the time required for the water level in the lake to drop by 1 centimeter. You are told that as the wind blows over the lake, assume it to be a turbulent boundary layer throughout. So, you can see that this is a typical problem. Say you have a power plant close to the lake, and you are drawing water from the lake for cooling in the condenser, and the hot water again comes back here, which mixes with the lake, but the lake water is continuously dropping, and therefore, you need to do topping up of this water from some other source nearby, and typically the groundwater source from nearby, so that the lake level does not drop too much and your power plant cooling operations are not hampered. So, you are told that the assumed turbulent boundary layer throughout, and take kinematic viscosity to equal to 15 into 10 raised to minus 6, sheet number equal to 0.67 and Prandtl equal to 0.7. So, in this case, corresponding to 40 degrees centigrade and 20% RH, we would evaluate PV infinity equal to 0.2 into saturation pressure, which is 0.07384 bar, and that will give us 0.01477 bar, and therefore, omega V infinity would evaluate to 0.00919, and therefore, taking Lewis number as equal to 1, which is fair assumption to start with, and if B is small, then it does not really matter too much, then omega V infinity divided by omega V W over omega V W minus 1, Hm infinity minus HMW, HMW minus HTL plus QL by NW. Now, here we do not know omega VW, that is the mass fraction at the surface of the lake, and therefore, we also do not know the mixture enthalpy at the surface of the lake, nor do we know QL. So, we have 3 unknowns. So, NWHT plus QRAD plus QL is equal to NWHTL. This would be the balance in the neighboring phase as usual, and therefore, BH would be Hm infinity minus HMW over HMW minus HT divided by QRAD by NW, and NW will be simply G into BH, and therefore, BH would be Hm infinity minus HMW QRAD by G divided by Hm infinity by HT equal to this value. What I have done here is I have replaced NW equal to GB and then multiplied through, so that BH gets cancelled and QRAD appears now in the numerator. So, if I now take T ref equal to 0, then Hm infinity would be 1.005 into 40 plus 0.875 into 40 plus 2503 into that omega V infinity value, which is 63.3. I do not know the surface of the lake temperature, therefore, I just keep it that H 1.005 TW plus 0.875 TW plus 2503 omega VW, and HT will be simply 4.187 into 30, which is the temperature deep inside the lake, and that is 125.4. Now, here U infinity is 10 kilometers per hour that has been given, which is essentially mean 2.78 meters per second, and therefore, the Reynolds number would work out to be 18.53 into 10 raised to 6, and therefore, we calculate for a 100-meter lake. We assume B tending to 0 and G tending to G star, and then for a turbulent boundary layer, the Stanton number would be 0.0365 REL to the power of minus 0.2 Prandtl to the power of minus 67, and that would be equal to 0.001617. Now, rho m, the mixture density will be equal to rho of the vapor plus rho of the air, which would be rho A into 1 plus specific humidity mean, which is the kg of dry air divided by kg of the mixture, and G star would be therefore 0.0049 into rho m. So, I have multiplied here by U infinity, which is 2.78. So, G star becomes 0.00449 into rho m, and Q rad over G star is 0.5 divided by 0.00449. This is Q rad is 500 watts, which is 0.5 kilowatts divided by rho m, and therefore, this will be 111.36 divided by rho m kilojoules per kg. And therefore, we have on substitution we will get B, which is from the mass fractions would be this, and from the mixture enthalpies it would work out to this value. So, we have to solve this equation iteratively. So, WVW corresponds to TW at saturation, and rho m is evaluated from W mean equal to WW by T plus W infinity. Now, of course, what you do is you assume TW and therefore, calculate WW, from which you calculate W mean, and therefore, you can calculate rho mean. Knowing WW, you can also calculate W omega VW, and then check whether the left hand side equals the right hand side or not. So, iterative calculations are required, and I have already given you a correlation for evaluating omega VW from TW. Alternatively, you can use steam tables or psychrometric chart, anything will do to evaluate, because we are only trying to discover the saturation condition at the wall temperature. So, these two left hand side and right hand side must be balanced by iteration. So, this is the trial and error procedure, and I have already explained to you how the trial and error is to be performed. So, in the present case, it works out to be TW equal to 39.5 degree centigrade, which is very close to the T infinity in fact, and omega VW turns out to be 0.043, rho m turns out to be 1.16, giving B equal to 0.0354. So, our assumption of using NW equal to GB here is not too bad, because B itself is very small. So, NW will be simply G star into B is equal to and G star we have already calculated. So, therefore, it is 2.035 into 10 to the minus 4 kg per meter square second, or 0.7324 kg per meter square hour. So, therefore, the lake water will drop. In order to calculate the lake water drop, what we do is rho water into delta H into surface area, A surface area. This will be the divided by delta T will be equal to m dot W, which is the surface area of the lake, and that will give us rho W into delta H by delta T equal to m dot W divided by A lake, and that will be equal to N W. So, we can now estimate, since we know now what the NW is, NW is we have evaluated as 0.7324. We take rho W equal to 1000 water delta H, which is 1 centimeter divided by delta T. So, if I evaluate that, delta T will be equal to 0.7324 divided by 10, or 0.07324. And that is what you get, or in terms hours, sorry, beg your pardon, here it will be 0.73 324 is on the right hand side, delta H is 0.01 into 1000, and therefore, delta T will be 1000 into 0.01 divided by 0.7324, which gives you 13.65 hours. So, of course, what we have done here is that for the whole day, over the entire period of this time, we have said the solar radiation is constant, which of course is not the case. The solar radiation varies during the day, but we have taken an average value, and we find the time required for 1 centimeter drop of the lake would be about 13.65, which is assuming sunshine hours of about 10 hours, we can say it is about 1.5 day would be required to reduce the lake water by 1 centimeter. Now, such estimates are very useful for estimating the top of water required in the lake, so as to maintain it in its level constant and not affect in any way the cooling water provision for the power plant. We now look at the final problem, and this time it is an internal duct flow problem. So, moist air at inlet specific humidity of 0.003 at 24 degrees centigrade enters a tube which is 2.5 centimeter diameters and 0.75 meters long. I beg your pardon, it is 0.75 centimeters, but it is actually 0.75 meters long at the rate of 9 kg per hour. The tube wall is maintained at 24 degrees centigrade. So, it is the same temperature as this. Calculate the specific humidity at exit from the tube and the heat supplied to the tube wall to maintain its temperature at 24 degrees centigrade. Take D equal to 0.09 meter square per hour diffusivity and Schmidt number equal to 0.6. Assume temperature remains constant throughout. So, even at exit the temperature is going to be at 24. So, in this case omega V W is constant with x because T W is constant with x, and therefore, if we define B x as I said in internal flow, omega V x will be the bulk value of the mass fraction minus omega V W divided by omega V W minus 1. So, if I take a differential d omega V x will be equal to omega V W minus 1 into d B x. If I now look at this small differential element of length dx, then mass transfer N W multiplied by the perimeter, which I take as dx. The perimeter is pi d in multiplied by dx would be the area. So, N W dx will be equal to m dot into change in mass fraction, but the perimeter value here is taken as pi d in the denominator here. So, N W dx into m dot by pi d d omega V x. If I substitute for omega V x this expression, I get an N W equal to G B dx, then I get G B x times dx equal to m dot divided by pi d omega V W minus 1 d B. On the next slide you see d B x by B x would be equal to pi d G m dot W omega V W minus 1 into dx. If I integrate this equation from inlet to outlet, then this will give me logarithm of B out over B in equal to that expression into L. So, that simply becomes pi d G L m dot omega V W minus 1 with an exponential sign. Of course, since omega V W is going to be less than 1, this quantity is negative, and therefore, exponential of a negative is a fraction, and therefore, B out will be less than B in, and L is the length of the tube. So, in this problem corresponding to 24 degrees centigrade, omega V W is 0.01875, W W is 0.01632, and corresponding to W in equal to 0.003, W V omega V in will be 0.0029991, and therefore, B in is 0.1606. We now determine G. Now, at inlet the mean value of the specific humidity will work out to be 0.01088, because we know W W and we know W in. At 24 degrees centigrade, rho air is 1.189, and therefore, rho m will be 1 rho A into 1 plus W m equal to 1.202. and then for nu m will be Schmidt number into d, which is 0.054 meter square per hour, or 1.5 into 10 to the minus 5 meter square per second. And therefore, now the mass flow rate is m dot into u in into pi by 4 d square, and therefore, u in will be 5.09 meters per second, and therefore, I evaluate Reynolds number as 8,488. Now, if I take Lewis number equal to almost 1, then I can evaluate Sherwood number from the Ditters-Boelter relationship as 0.023 Reynolds raised to 0.8 Schmidt number raised to 0.4 as 26.06, which gives me G equal to 112.76, and therefore, the substitution in here. Now, I know pi, I know the diameter of the tube, I know G now, which evaluated at 112.76 kg per meter square hour. M dot is 9, L is 0.75 meters, and omega VW is already known as 0.01875, which gives me B out equal to 0.00757, and we had evaluated B in equal to 0.01606. So, I can see that B out is actually smaller than B in. Now, omega V out will be omega VW plus B out omega VW minus 1 from the definition of B out, and it will be 0.01137, and therefore, the specific humidity at the outlet would be 0.01145, because knowing omega V out, I can evaluate W out. So, you can see, whereas W in was 0.003, as you can see, the specific humidity at inlet was 0.003, but now the air has been humidified, and the specific humidity at outlet is 0.01145. So, air has indeed picked up moisture from the surface. Now, if I do energy balance, then you will see m dot into change in enthalpy would be equal to the mass transfer from the surface HTL minus QL, which is the conduction heat transfer or the heat away from the wall, into pi d dx, which is the perimeter of the tube into dx. So, if I integrate now this expression for QLX, then I will get minus Q bar L equal to minus 1 over L 0 to L QLX dx, which will be m dot by pi d 0 to L dHm by dx minus GHTL 0 to L Bx dx, which will give me m dot pi d into Hm out minus Hm in minus HTL omega V out minus omega V in. And therefore, you will see taking T ref equal to 0, Hm out will work out to 52.82, because we know T out is also 24 degrees centigrade. We already know omega V out. So, we can work out omega Hm out. We can work out Hm in, which is the inlet condition, and HTL is 4.187 into 24, therefore 100.49, and that gives me Q bar L equal to minus 0.646 kilowatts per meter square. Negative sign indicates that the heat must be supplied to the tube, and so this is the second answer to our problem. So, we do find that in the tube the specific humidity has increased and the temperature has been given as constant. There is no change in temperature of the air, in which case you will have to supply heat to the wall, so that it is maintained at 24 degrees centigrade, and the value has been found. So, you can see we have used psychrometry in variety of applications like wet bulb thermometer, mass transfer from a porous surface, which is to be kept at a specified temperature. We have looked at flow humidification of air in a tube, which has to be kept at a specified wall temperature, and we also looked at amount of water depletion that would take place due to evaporation, convective evaporation due to wind, as in the presence of solar energy. So, a variety of problems can be solved by using Reynolds flow model in our Reynolds flow model, and you can see it's a very convenient tool. We have not solved any differential equation. We have simply made use of the available correlations to get the appropriate value of G star in each case.